The photoelectric effect. A metal with work function of phi is used in the photoelectric effect experiment. Light with intensity I and wavelength lambda strikes the metal surface to eject photoelectrons with a maximum kinetic energy Kmax. Part A, sketch the experimental setup showing all the circuit elements. Okay, so here is the experimental setup. We have two metal electrodes. One is the cathode, the other one is the anode. We send light onto the cathode. The photoelectrons are ejected, cathode gets positively charged, and they travel towards the anode inside a vacuum tube. So there is no other gas inside this tube that may be ionized due to the presence of these electrons. So the electrons basically travel directly from the cathode towards the anode. The current that flows in the circuit is monitored with an ammeter here. So this is measuring the photocurrent, and we apply a variable potential with respect to the anode. So cathode with respect to the anode potential I called V, and it's variable. So when I apply a certain negative potential to the anode with respect to the cathode, these electrons will be stopped. That will be called the stopping potential. So that's the experimental setup. Part B, according to the classical theory, how would the maximum kinetic energy of the ejected electrons change if the intensity I is doubled and the wavelength lambda is halved? Okay, now, what is intensity? Intensity of light is the average power delivered per perpendicular area A. So that's the perpendicular area. And that means this is 1 over the perpendicular area A, average value of the energy delivered per unit time, dE dt. Now, if the intensity is doubled, then in the same time interval, you would have delta E becoming 2 delta E in the same time interval. Okay, so what does that imply for the maximum kinetic energy of the electrons? The classical theory says the electron energy is delivered by the incoming electromagnetic waves. The energy that we are delivering, delta E, is becoming 2 delta E. So one would say Kmax will be doubled. It will become 2 Kmax. But we also have this requirement that part of this energy will go into the binding energy of these electrons. So it will take some time and some energy to eject these electrons, and then they will have a kinetic energy. So this energy that we're delivering is not just going to kinetic energy. It's also taking care of the potential energy that keeps these electrons in orbit inside the metal. Due to finite absorption time and the binding energy and the potential energy, in fact, the maximum kinetic energy will be less than doubled. The wavelength lambda has no effect. It doesn't enter these equations. So basically, by increasing the intensity, we have only a change in the energy that we're delivering per unit time, And this energy, because partially goes to the potential energy of the electrons and there is a finite absorption time, the increase in the kinetic energy will be less than twice. So it will be less than doubled. Okay, part C. Experimentally, how does the stopping potential change if the intensity is doubled and the wavelength is halved? Okay, so if the wavelength becomes lambda over 2, this means because we have a constant propagation speed of light, the frequency will be doubled, frequency will become 2f, and the photon energy, hf, minus the work function, the potential energy of the electrons, will be equal to E times delta Vs, which is the maximum kinetic energy. So this is H now becoming H times 2F. The work function doesn't change and we have a change in the stopping potential. So you can see that the stopping potential will be less than doubled. Intensity I has no effect on the stopping potential. That's the experimental result. The stopping potential will be less than doubled. Part D, that's due to the presence of this work function here. Experimentally, how does the photocurrent change if the intensity is doubled? So the effect of increasing the intensity, I becoming 2I, is basically increasing the number of photons that interact with the electrons. So since this is a one photon, one electron process, what we will see is that the number of ejected electrons, photoelectrons, will be doubled because we have doubled the number of photons hitting the surface per unit time. Now the photo current, IP, that can be written as the electron density, photoelectron density, electron charge, the drift velocity multiplied by the area of the cross-sectional area of the wire. The electron density, number of electrons per unit volume, N will be doubled, and the photocurrent therefore is doubled. So the ammeter will measure twice the original photocurrent when the intensity is doubled. Part E. If the experiment was conducted on a special metal with zero work function, what would be the cutoff frequency? This is impossible, but let's say that it was possible. Then we would have H times the cutoff frequency Fc minus phi is equal to 0, the maximum kinetic energy of having a maximum kinetic energy of 0. We would have a cutoff frequency Fc is equal to the work function phi divided by Planck's constant h equals to 0. So we would have the 0 cutoff frequency if it were possible. Okay, so we have talked about the photoelectric effect. Photoelectric effect is conducted with the setup. We have a cathode and anode. We shine light on the cathode. Photoelectrons are ejected from the cathode, travel towards the anode without interacting with anything else because it's inside a vacuum tube. And we measure the resulting photocurrent with an ammeter, and we have a variable voltage being applied of the anode with respect to the cathode. According to classical theory, if you have intensity doubled, that means we're doubling the energy we deliver per unit time, per unit cross-sectional area, perpendicular area, because part of this energy goes to the potential energy, so to the energy required to release the electrons from the metal. That's basically the work function, and we have a finite absorption time for the absorption of this energy. We will see that the maximum kinetic energy is not expected to be doubled, but it should increase. It should be less than doubled when the intensity is doubled, and the wavelength should have no effect. In part C, experimentally, how does the stopping potential change? Well, E times the stopping potential is basically the maximum kinetic energy. Experimentally, decreasing the wavelength to lambda over 2 means increasing the frequency to 2f. We have h times 2f minus phi is E times the new stopping potential, and because of the presence of this work function here, the stopping potential will be less than doubled. The intensity will have no effect. In part D, when the intensity is doubled, how does the photocurrents change? Doubling the intensity experimentally, the number of photoelectrons will be doubled because the number of photons hitting the surface per unit area per unit time will be doubled. It's a one photon, one electron process, and energy HF is absorbed by the electrons. Part of that energy goes to the work function and part of it goes to the kinetic energy. And that means the electron density N is doubled and photocurrent will be doubled. So the number of photons is doubled, the number of photoelectrons is doubled, the resulting current is doubled. In part E, if it were possible to have a special metal with zero work function, what would be the cutoff frequency? Well, the cutoff frequency is work function phi divided by h, and if phi is 0, cutoff frequency would be 0. So we would have at cutoff the onset of a photocurrent. That means we have a 0 maximum kinetic energy of the electrons.